In this next section, we're going to look at the definite integral from a different perspective. And in this case, we're going to look at it from some graphical representations. But before we do that, I want to talk a little bit about the fundamental theorem of calculus. Fundamental theorem of calculus is what we're going to use to set up and evaluate a lot of our properties for definite integrals. So all of those properties we had when we first started talking about antiderivatives, we're going to use again when we have actual limits on our function. And so the fundamental theorem of calculus is going to tell us how to do that. Okay? The fundamental theorem has two parts to it. And the first part is what actually defines the antiderivative in relationship to the interval that we're looking at. So given a function that's continuous on an interval, ab, and f of x, this capital F of x, that's any antiderivative of f, then the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay. And again, like I said, we're going to use that for a lot of our properties. So all of our sums and differences, our constants, power rules, all of that stuff, we're going to use it to find an antiderivative and then evaluate over the interval. Okay. The second part of the fundamental theorem I'm going to mention here, and we will see a couple of examples of it within the exercises. Outside of that, we're not going to use it a whole lot. It is more useful for the science-based calculus classes that are going to go on to do a lot more with integration than what we're going to do. But basically it says that, again, if I have a continuous function that has an antiderivative, then the derivative of the antiderivative should equal the integral over a basic unit interval, the unit being from 0 to x. Okay? Notice here my function is in terms of t, so if I evaluate this integral, I'm going to get an f of x, a capital F of x minus a capital F of 0. And then f of 0 is just a constant, so I'm just looking at capital F of x, right? So this would be based on the first part of our fundamental theorem. And then if I look at this and derivate it, well, the derivative is basically going to be the derivative there, because the f of 0 will go to 0, or yeah, goes to 0 as I take the derivative. So this just gives us a relationship between derivation and integration. And it shows that they really are inverses of each other. Okay. Like I said, we won't use that second part so much, but we'll definitely be using the first part of the fundamental theorem. Okay, so let's step away from that for just a second, and let's look at some graphical representations of our definite integral. Okay. If f of x is greater than or equal to 0 for all x, so what does that mean? Well, it means that my function is entirely above the x-axis on the interval a to b. Then f of x dx, the integral of that from a to b, is equal to a, where a is defined to be the area of the region bounded by y equal f of x, y equals 0, x equal a, and x equal b. And so pictorially what this is saying is if I have some function f of x and I have some interval from a to b, notice here the x-axis is my curve y equals 0, then what this is saying is that definite integral is that region between those curves. Okay. Now, some other things to consider are other properties in terms of this graphic representation. Well, the first is one that we won't use so much, but it does come up, okay? And that is if I'm looking at, again, some function that's entirely above the x-axis, and I look at a point, so not an interval, but just a point, then what this is saying is that the integral from a to a of f of x dx, meaning the area under f of x over the region described by a, well, there's no length there, so this is just going to be 0. Okay. If I look at the integral from b to a of f of x dx, okay, now you'll notice I set up this picture the same as I did before. A is to the left of b, and my function is still entirely above the x-axis. The only difference is I'm looking at the interval backwards. So if I look at starting at b and then going to a of this integral, what this says is that this area is basically going to be the negative of the interval from a to b of f of x dx. And why we get that negative is, again, if I think of that fundamental theorem, it says I'm going to always evaluate at this upper limit minus the lower limit. So if I reverse those, it's going to be backwards, and I'm going to have an extra minus sign. So to make them equivalent, I need to put a minus sign in there. Okay. And I'm going to squeeze one more in on this side, and that is, let's say there's my function f of x, and my interval from a to b is there. Okay. Now in this case, my function is not entirely above the x-axis. And so if I want to find this area, meaning looking at the region between that and the x-axis on both parts, then here my area is going to equal the integral. We've got to find this point in here, which I'm just going to call c. It's going to be the integral from a to c of f of x dx plus the integral from c to b of negative f of x dx. Okay. And this is what's going to help us take care of regions that are below the x-axis. So I can still find the area, and the area, obviously an area in general, is always positive. But if I just take this region from c to b as is, and I say the integral from c to b of f of x, I'm going to get a negative number, and that's not going to make sense in terms of the area. And so here I'm going to have to split the positive and negative pieces and treat the negative pieces a little differently. Okay. So another representation that we'll see is one such as this, where I have more than one curve. And we're going to deal with these a little bit more in Chapter 7, but it falls under these graphical representations very similarly to this last example we showed. Okay. So if I have two functions, an f and a g, where f of x is bigger than or equal to g of x for all points on a curve or an interval, a to b, then a, again being our area, is going to be defined this way. And so again, kind of the graphical representation here is if this is my f of x and this is my g of x, and here's my interval from a to b, then to find the area of that region, I'm going to subtract the f minus g over that interval. And once I get that antiderivative, plug in my limits, and that'll give me my value. Okay. And I have one last picture to put up here. And that's the case where, again, I have two functions, but it's not entirely one is not entirely greater than or equal to the other for the entire interval. Okay? And so here we would see something like, let's say this is our f of x, and this is our g of x, and let's say there's our a, and there's our b. Okay, so if I want to find this area, again, over that interval, I'm looking at those two regions. So again, similarly to that last example over there, I would find this value c, and my area would be defined by the integral from a to c of my f minus g plus the integral from c to b of my g minus f. And so for these, it's just, again, keeping in mind for all of our areas, we're always thinking kind of an upper curve minus a lower curve, and we're always going to evaluate at the upper limit minus the lower limit. Okay? And that's basically what our fundamental theorem of calculus says. So we'll use the intervals as well as the function's antiderivative to come up with the area of the graph.